Alright, hi there everyone. Welcome back to another episode of CS341, where we're going to be talking about dynamic programming for the last time. And then next lecture we're going to switch over and Anna's going to take over for me. Okay, so the first thing we're going to talk about today is a problem called the longest common subsequence problem, or the LCS problem. So what's the longest common subsequence? Well, an input instance is going to consist of two strings, x and y. We'll call them sequences, but there's no real difference between a sequence and a string. A string is just an array of characters, and a sequence is an ordered array. So we have x, which consists of the characters x1 up to xm, and we have y, which consists of the characters y1 up to yn, over some finite alphabet gamma. So each of these characters is drawn from gamma. And we don't have a restriction on how big gamma can be, but it has to be finite. And intuitively, in most cases, you would think of gamma as being relatively small, like, the English alphabet, for example. And the goal in the LCS problem is to find a sequence Z of maximal length that is a subsequence of both x and y. Okay, well, what's a subsequence? So if you take the string x and you delete some number of characters from it, what you are left with is a subsequence of x. You'll have some of the characters that were in x, and they'll be in the same order as they appeared in x. You've just deleted some characters in between. So you can think of obtaining a subsequence of x as taking x and deleting some number of characters from it. And you can think of a subsequence of y as just y having deleted some characters. So we want to find the longest possible z that appears in both x and y, meaning it's a subsequence of x and it's a subsequence of y. In other words, we want to find the longest possible z such that we could delete characters from x to obtain z and delete characters from y to obtain z as well. This is the longest common subsequence of those two strings. And I have a formal description here. Okay, so ultimately we want to solve for the longest common subsequence, meaning we want to actually output the longest common subsequence itself, the string that is the longest common subsequence of x and y. But before we actually output the string, let's solve for the problem of finding the length of the longest common subsequence of x and y. I want to start out with a couple of examples here. So here are some example strings, x and y. So here, if x is a, and y is b, what is the longest common subsequence of x and y? I'll give you a second to think about that. Okay, I'm going to assume that you've paused and answered that if you wanted to. So they have nothing in common. There are no characters in common. So the empty sequence, epsilon, is z. Z is the empty string, or the empty sequence. Well, how about this example? We have A, B, C, D, E, and we have B, C, D. Okay, so I'm sure you can answer this. The longest common subsequence is B, C, and D, because if I delete A and B from X, I'm left with B, C, D, and if I delete nothing from Y, I'm left with B, C, D. So when I say you have to delete some characters from X and from Y, you can delete 0 characters. That's fine. Okay, so B, C, D is the longest common subsequence of X and Y. How about A, B, C, D, E and L, A, B, E, F? This is just me typing label wrong, labef. Okay, so what's the longest common subsequence of this? What do you think? So I'm going to assume if you wanted to answer that, you've done so. So we can see A appears in both, followed by B, followed by E, although the E has a few characters in between it and the previous character B. So A, B, E, we can delete C and D, and we can delete L and F, and we end up with A, B, E in both strings. So that is the longest string that we can obtain by deleting characters, 0 or more characters from X and Y. So that's the longest common subsequence. I have to wait 1 second. My computer's pausing here. Okay, so could you solve the longest common subsequence problem with a greedy algorithm, perhaps? It sort of seems like it might be plausible at first glance, right? So here's a possible greedy algorithm. Suppose for each character in X, we try to choose a matching character in Y that's to the right of all previously chosen matching characters in Y. So let's try to run it on this pair of strings that we just saw and see if it comes up with the optimal solution. So we'll start with the first character in X, A, and we'll try to find a matching character to the right of all previously chosen values in Y. Well, there are no previously chosen values in Y, so we'll just find the first character, the first occurrence of A. Okay, we'll match those up, and we'll go to the next character of B, and we'll try to find a matching B in Y to the right of A. Okay, we found one. Now we'll go to C, and we'll try to find a matching C to the right of B. Well, there is no matching C. Then we'll try to find D. There's no matching D. We'll try to find an E to the right of B, and we do find the matching E. Okay, so in this case, the proposed greedy algorithm came up with the optimal solution, ABE. Is this always optimal? So I'll give you a moment to pause here, see if you can come up with a counterexample for this algorithm. In other words, try to come up with an example for which this algorithm does not find the longest common subsequence of X and Y. Okay, so I'm going to assume you've paused and done that if you wanted to. So let's see such a counterexample. So here we have, I've taken the very magical sounding word abracadabra, and I've put a Z in right after the A here. And then I've put a Z at the end in Y. So we have asbracadabra, tongue twister, and abracadabras. Okay, so let's see what the algorithm does when we run it on this pair of strings. So for the first character of X, we'll find a matching character on the right. For the second character of X, we'll try to find a matching character on the right that's to the right of all previously chosen letters, so to the right of A. Okay. Now we'll try to find a B that's to the right of the Z that we found. Well, there's nothing to the right of the Z that we found, so it can't find a match for this B, or this R, or this A, C, A, any of the other characters. There will be no further matches. The fact that the Z that we greedily tried to take into our potential longest common subsequence was found right at the end of this Y string messes us up. So we're going to end up with Z equals AZ. And this is clearly not the longest common subsequence, right? Because we can find abracadabra in both of these strings. Okay. So is there a greedy algorithm that'll solve for this case? Well, we could actually take the greedy algorithm that checked all of the letters of Z moving from left to right, and we could flip it so it checks all the letters of X, all the letters of X. Instead of checking them from left to right, we can check them from right to left, and that greedy algorithm will actually find the optimal solution for this example input. However, it's not hard to modify this example input so that algorithm fails. And indeed, I'm not aware of any greedy algorithm for this problem, and I would be very surprised if there were a greedy algorithm for this problem. So blindly taking Z here is bad because we end up matching it very far on the right, and then we can't continue after that point. How should we decide whether to take or leave Z in this case? So in dynamic programming, we could maybe try both possibilities, right? Whereas in greedy, if we take it, then we can't later try not taking it. Our decision is irrevocable in a greedy algorithm. In dynamic programming, we could try both, and we could, take the max of both options, something like this. So we can try all possibilities using dynamic programming, and that's going to help us get an optimal solution. And it turns out the runtime will be actually quite reasonable. Okay, so the first step if we're going to take a dynamic programming approach is we have to try to define subproblems that we're going to solve. So let me just state the full problem here before we state subproblems to make sure we're on the same page. So the full problem is going to be to return the length of the LCS string itself. So the length of the string, the length of the LCS of X and Y. And a natural way to define subproblems here would be to somehow shrink X and Y, so we're dealing with smaller input strings. So in our case, we'll reduce the size of X or Y by taking prefixes of X or Y. So let me define some notation here. Xi is going to be the prefix of X of length I. So it's going to be the first I characters of x. So I've drawn xm here, which is the whole string x, and then x4 here is just the first 4 characters, right? And similarly for y, yi is the first I characters of y. And of course, we said that x has length m and y has length n. So x is just xm, and y is just yn. So our subproblems are going to be returning the length of the LCS of xi and yj for all the different i's and j's. Those will be our subproblems. And how are we going to try to relate our optimal solution to the full problem to optimal solutions to subproblems, to try to find this recursive optimal substructure that we can use to solve dynamic programming, solve this in a dynamic programming way? Well, here's an idea for our recurrence. We can try to do something with the last letter of x or y, and we can try to reduce the problem, you know, xi yj to like xi minus 1 yj, or like xi yj minus 1, or xi minus 1 yj minus 1, something like that. So we'll try somehow cutting off the last letter of x or y. And I'm going to try to explain how we do that by working from a couple of different examples to build intuition. So suppose we have this example string here, x, which is abracaz, A-B-R-A-C-A-Z-Z, and then y is going to be A-Z-B-R-A-C-A-D-A-B. This is asbracadab. Okay, and here in these two example strings, x and y, you know, the last letters don't match. Z and B don't match. Now, here I'm going to write the indices here so we can tell what indices these represent. In this case, m is however many digits this is. This is 8 digits, so m is 8. And so it's x1 up to xm, and this is y1 up to yn. Okay, so these are the names of these individual characters, the indexes of these individual characters. Okay, and I want you to consider, because we're always trying to relate an optimal solution to the optimal solution to subproblems, I want you to consider the optimal solution z, which is the LCS of x and y. Okay, so just by inspection, we could look really carefully at this, and we could see that the optimal solution, the LCS, is going to be ABRACA. Okay, so it's going to be 6 letters here, and we're going to call this Z, and its letters are going to be Z1 up to ZL, in this case Z6. Okay, so we don't know this optimal solution until we solve the problem, right? But we can still imagine the optimal solution and reason about it, similar to how we did in the other dynamic programming problems that we've seen so far. So I want you to look at this example. So I know this is just a concrete example, but let's see, in this concrete example, the last letter of x does not match the last letter of y, and neither of them match the last letter of z. So remember, z is the longest common subsequence of both of these strings, so z appears as a subsequence in both of these strings. So this a, the last letter of z, should appear somewhere in x, and indeed we can see it appears here. And it should appear somewhere in y, and we can see it appears here. Or maybe it's this a. Hard to tell because there are lots of a's as extra letters in this y. Okay, so this a certainly is not the last letter of x in this example, right? Because it's a z. This can't be the final a in our LCS string. Now, z is a subsequence, as I mentioned, of x. So that a has to appear somewhere here in the prefix xm minus 1, the prefix where we've chopped off the last letter. And this last letter can't be used at all in the longest common subsequence. Okay, so now if we turn our attention to y, similarly, this last b in y, the last letter, it doesn't match the last letter of z. So this can't be the final a that we're looking for in the LCS. So just like in the case where we just talked about x, this last letter of z, because z is a subsequence of y, it has to appear in this prefix of y. The entire subsequence z has to appear in the prefix yn minus 1. So this a has to be back here somewhere in yn minus 1. So it turns out we don't need this final b in order to compute the LCS, because the entire LCS can be found in this prefix of y. Similarly, we don't need this final z, because the entire LCS can be found in this prefix of x, xm minus 1. So neither of these letters is part of z. So if this is true, if the last letter of x does not match the last letter of z, and the last letter of y does not match the last letter of z, then we know that the LCS z we're looking for can be found in xm minus 1 and yn minus 1. So the LCS will just be the LCS of xm minus 1 and yn minus 1. Okay, so this is the case where the last letter of x and the last letter of y do not match the last letter of the optimal solution z. Here's a second case where the last letter of x does match the last letter of z, but the last letter of y does not. Okay, so this might be the final a in z, or maybe this is. At any rate, we don't want to chop off this a and recurse on a smaller prefix of x because we might need this a. Okay, but this b at the end of y is certainly not the last a in z in this case. This doesn't match the last letter of z, so we don't need this letter because the entire LCS z should be found in y, and the last letter can't be this last letter b, so the entire LCS should be found in the prefix yn minus 1. Okay, so in this case, in order to find the LCS, we can just invoke LCS x, y, n minus 1, okay? So we can solve the subproblem x, y, n minus 1, and we'll end up with the same LCS. If this condition is true, that the last letter of x matches the last letter of z, and the last letter of y does not match the last letter of z. Okay, and the symmetric case, where the last letter of x doesn't match the last letter of z, but the last letter of y does, that case is symmetric. And so in that case, the LCS will just be the LCS of xm minus 1 and y. So we'll chop off. In that case, we'll chop off the last letter of x because it won't match. In this case, we chop off the last letter of y because it doesn't match the last letter of z. Okay, and for a final case, okay, so we saw neither last letter of x or y matches the last letter of z. We saw one of the last letters of x and y match the last letter of z. Let's see both of the last letters of x and y match the last letter of z. So in this case, this last letter of x might be the final a in z. Or maybe one of these earlier ones, maybe one of these earlier a's. But we can't chop this off because we might need it. Similarly, this final a might be the final a in z, so we can't chop it off because we might need it. I mean, we can see in this particular case by counting a's and, just sort of staring at the string that we don't really need this a. But the thing is, without doing a lot of computation on the string y, that would end up taking a really long time if y is very large, you can't tell that this a isn't needed. So naively, because this a matches this last letter of z, we might need it. So how do we get around this problem where it seems like we can't shrink the problem size at all because we can't chop off this a, we can't argue it's useless, and we can't argue this a is useless, so we can't shrink either x or y to a prefix? Well, in this case, we know that the last letters of x and y match each other and match the last letter of z. So why not just consume xm and yn by matching them both with zl, and now we won't think of finding the entire LCS in a subproblem. We'll match these two a's with this a, and we'll think about finding a smaller part, a prefix of the LCS, in a prefix of a and a prefix of x and a prefix of y, okay? So the LCS of x and y is going to be the LCS of xm minus 1 and yn minus 1 plus this last a that we found and matched ourselves. So this is the generalized formula here. So the LCS is just going to be the LCS of xm minus 1 and yn minus 1 plus that last letter that we just matched with these two characters at the end of x and y. Okay, so let me summarize these cases. So we just saw the last character of z matches neither of the last characters of x and y, in which case we chop off the last characters of x and y and recurse on smaller subproblems in each case. each of these is smaller. Or we see ZL matches one of these but not the other, and we chop off the one that doesn't match. That's these two cases. We chop off the last letter that doesn't match. Or ZL matches both XM and YN, in which case we match XM and YN, so we add it to the LCS and we recurse to find the rest of the LCS, the prefix of the LCS in XM-1 and YN-1. Now the problem is we have 4 cases where we have different expressions, and the case that we should pick depends on which of these statements is true. These are statements about the optimal solution, but we don't know the optimal solution. If we knew it, we'd be done. We'd just print it, right? So we don't know ZL, so how do we figure out which of these cases we're in? Well, intuitively, in the past when we've had this problem, we've tried all of the cases and maximized over all of the cases, right? So we're going to do something like that here, but you have to be a little bit careful because this last case is only valid if XM and YN match, right? Because we matched those 2 letters and we said, okay, now we're going to add that letter to the LCS. So this last case, we need XM to be equal to YN. Okay. Now, additionally note, and this is a little bit tricky, so bear with me, XM is equal to YN only in this last case. In each of these 3 previous cases, XM is actually different from YM. Let's argue that that's the case. So in cases 2 and 3, where ZL matches one of XM and YN, but not the other, this is trivial, because if XM was equal to YN, ZL would match both of them. So in each of these 2 cases, it's easy to argue that XM is different from YN. But what about here? ZL matches neither XM nor YN. It could be that ZL is like A, and XM and YN are both B. But if A is the last letter of the longest common subsequence, and both of these are B, we could match up those B's and add them to the longest common subsequence to improve it. But that's a contradiction because the longest common subsequence is the longest common subsequence. We can't extend it by adding a B at the end. So, since we can't improve the longest common subsequence, we can't have XM equal to YN. So in each of these 3 first cases, XM is different from YN. Okay, so I've copied the recap from the previous slide, plus I've annotated it with these XM not equal to YN and XM equal to YN bits here. Okay, so let's try to derive a recurrence using these expressions. So we had to be a little bit careful because we could only use this last expression, we could only include it in a max if it was valid, if we actually had an XM that matches YN. For the rest of these 3 expressions, XM is different from YN, and there's no such constraint that we have to make sure we have a matching XM and YN in order to include these in the max expression. It's perfectly safe to include these in the max expression. The LCS we're looking for will be the max of all 3 of these, and if XM is equal to YN, it'll be the max of all 4 of these. Okay, so let Cij be the length of the LCS of Xi and Yj. This is what these are the subproblems we're going to try to solve. Cij is going to be our recurrence. Here I'm defining the meaning of the recurrence, and then we'll show how to actually compute the recurrence. So the meaning of Cij that we're trying to compute here is the length of the LCS of Xi and Yj. Now let's brainstorm a sensible base case here. So Cij, well, what values of I and j would make sensible base cases? Remember, I, j become xi and yj, and these are the prefixes of x and y of lengths I and j respectively. Well, what about a prefix of length 0? That would just be an empty string, and then we would know what the LCS of the empty string and some other string is, right? What's the LCS of an empty string and another string? It's just 0. They can't have any letters in common. Okay, so, well, if I is 0, then one string is empty, so C of 0, comma j is just 0. And it's the same thing for j equal to 0, right? If j is 0, then, well, the yj string is empty. So we have C of I, comma 0 is 0 as well. So those are our base cases. And for our general cases, we're going to combine all of these expressions here at the top of this slide according to these two cases, xm equals yn and xm not equal yn. So if xm is equal to yn, then we're allowed to include this last expression in our max. So in this case, Cij is actually just going to be exactly this expression, right? Because this is the only case where xm is equal to yn. So we've argued already that the optimal solution, if xm is equal to yn, has to be this, the LCS of xm minus 1, yn minus 1 plus zl. Well, plus zl is a character. Here we're trying to compute not the LCS itself, but the length. So this zl is going to be replaced by a 1 because it's the length of that character, just 1. So we're going to have C of ij is C of I minus 1, j minus 1. So the best we can do with prefixes xi and yj is the best we can do with prefixes xi minus 1 and j minus 1 plus the one character that we matched. And if xm is not equal to yn, then one of these three cases apply, and we don't know which of those three cases apply, so we'll just take the max over all three. Okay, not too bad. So let's combine these expressions into a single recurrence of the form that we're used to seeing. So here, those expressions are just rewritten into a recurrence here with conditions written. We have the base case folded into the recurrence as well. And I can actually simplify this recurrence a little bit because if you observe that, so there are three terms here being maximized over, right? And this last term, C of I minus 1, j minus 1, that's a subproblem of each of these two terms. Each of these two terms is solving a larger subproblem than this. Because this, for example, I minus 1j, this is what's the LCS of the first I minus 1 characters of x and the first j characters of y. Well, that's going to be at least as big as the LCS of the first I minus 1 characters of x and the first j minus 1 characters of y. Okay, this expression on the right has actually more of the strings to work with, so it should be able to extract an LCS that's the same or larger. So this term here is always going to be less than or equal to this term on the right. And we're taking a max of 3 terms. So this term, which is always the same or smaller than this term, there's no reason to ever choose this expression. So we can actually delete it entirely from this recurrence without changing the result. So here's our simplified recurrence. Okay, so I want to give an example of actually computing the table of values here. First of all, what order should we compute our table entries in? Well, as you might expect, it makes sense to do the base cases first, right? So we can do the base case first, and then we have to ask which rows and columns are we referring to in our dependencies. As we try to compute Cij, we're depending on Cij minus 1, Ci minus 1j. So in this diagram, j is going down and I is going to the right. So j minus 1 is up 1. So we're looking at the cell above us. I minus 1 is to the left 1, so we're looking at the cell to the left of us. And I minus 1, j minus 1 is we're looking at the cell to the top left of us. Okay, so we depend on a cell up, left, and top left. So that tells me if I compute rows from the top down, from j equals 0 to j equals 7, and then within each of those rows I compute left to right from I equals 0 to I equals 7, then I'll have a solution that I'll have an order for computing these entries that always ensures when I'm trying to compute Cij, I've already computed Ci minus 1, j minus 1, Ci, j minus 1, and Ci minus 1, j. Because I've already computed the previous row, that knocks out this j minus 1 and this j minus 1. And then within this row, I'm computing left to right, so I've computed my smaller I value already. Maybe it's more confusing to think about up and down, left and right. You should just think about the numbers. So I want to compute smaller j first, okay? And I want to compute smaller I first. So I from 0 to n, j from 0 to n, or sorry, 1 to n in each of those cases. Oh no, 0 to n. Confusing myself. We do have a 0th row and column, thanks to our base case. Okay, so as you might expect here, this first row is j equals 0. That's just 0, and the same thing for this first column. I want to give you guys as an exercise here a few of these table entries to fill in, and in a second I'll explain the computation. So why don't you take a look at this recurrence and try to compute manually Q3, 4, 5, 6, and 7's values. I'll give you a second to do that. Okay, so I'm going to assume if you wanted to do that, you have. Let's see how those computations work. So for Q3, we need to figure out which case we're in. We're not in the base case anymore, so we're in one of these two cases. And these two cases differ based off of whether xi is equal to yj. Okay, so what's our xi? Well, if we go up to, this is our I values, right? Here's x, so xi is g, and yj is g. They're equal, so we're in this case, so we're going to look at the top left cell to the top left of us, and we're going to add 1 to that. So 0, that's going to become 1. And then for Q4, we're going to ask the same question. Are our xi and yj equal? G is not equal to v, so now we're in this case. We're going to take the max of the cell above us and to the left of us. Well, that's going to be 1, right? And here we're going to do exactly the same thing because c is not equal to g. So we're going to take the max of 1 and 0, that's 1. And then, of course, we can compute the rest of these. I'll just fill them in. Now here for Q6, we have v, which is not equal to g. So we're going to take the max of above and to the left, which is 1. And here in Q7, we have v equal to v. So we're going to take the top left plus 1, because we're in this case. So we have 1 plus 1 is 2. So you can sort of see how the number is growing. The number grows every time we go down to the right, right? And it stays the same, it just gets propagated by this last rule, right? Okay, so there's the rest of the values, and you can see once we get to the end of the x string and the end of the y string, in the bottom left we have the LCS length, the longest common subsequence length of 4 of both of these. So what's the longest common subsequence of GD, VE, GTA, and GV, CE, KST? Well, C, K, and S don't appear, so we're going to get GVET, GVET. Yep, they occur in both those orders. So GVET is the answer, and its length is 4. Okay, so here's the pseudocode for this LCS algorithm. All we really do is take this recurrence and then try to implement it with a table. So our table is going to look just like our recurrence. We have a recurrence with 2 arguments, I and j, that vary between 0 and well, I varies between 0 and m, and j varies between 0 and n. It's not 1 to n and 1 to m, it's 0 to m and 0 to n because we have this extra base case row and column. And we're just going to perform our base case first. That's these 2 for loops. And then this last pair of nested for loops is going to compute all of the non-base case values, all the values of those subproblems. So we're going to compute cell ij, and we're just going to check which case we're in, if xi is equal to yj or not, and we're going to just implement these 2 different cases of the recurrence. And then the final answer that we want is CMN, because what's our semantic definition of C that we claim we've implemented here? Well, the semantic definition of C is the length of CMN is the length of the longest common subsequence of xm, which is just x, and yn, which is just y. Okay, so it's the length of the longest common subsequence of x and y. That's exactly what we want to return. Okay, so what's the complexity? Let's think for a second about the complexity of this algorithm. And I want to think about both time complexity and space complexity, and let's just think about the word RAM model. So why is the word RAM model reasonable here? Well, we're talking about strings of characters, and characters aren't huge numbers like Fibonacci numbers, right? There's no reason to think that we're probably going to be working with a gigantic alphabet where you can't even fit a character into a single word, right? So we're thinking of characters being relatively small numbers here. So the word RAM model, I think, is reasonable here. So in the word RAM model, accesses to a word, in this case accesses to a character, take order 1 time, right? So I can do a lot of these steps here. I can read cells of my table in order 1 time. I can do these subtractions and additions in order 1 time. I can do the max in order 1 time, and so on, right? So the time complexity here is going to be constant time per per iteration of the loop, so that's order mn time for these two nested loops. And then this first loop is going to be order m time, and the second loop is order n time. So order mn time dominates this whole expression. How about the space complexity? So I haven't focused a whole lot on space complexity, but space complexity is the number of words that are used, in this case, by the algorithm, excluding the input. So we'll ignore the input. How many words are we using in this algorithm over and above the input? So we're using I, J, well, that's just, a couple of extra words, right? Kind of irrelevant in the calculation here. C is the biggest source of words, and there are m times n words in C, right? So the space complexity here is O of mn words. Okay, so hopefully that makes sense. I think I'm not going to go into a huge amount of detail on it in this lecture, but I want to point out at the end of the deck of slides for this week, I think I have 4 or 5 educational slides that should be helpful for just clarifying and reviewing a few of the models and clarifying some of the complications that students have asked about in Piazza. I'll try to clarify a little bit of the uncertainty in how you should be computing runtime and space complexity and input size for the word RAM model and the bit complexity model. Okay, so we'd like to be able to compute not just the length of the LCS, but the string itself. We'd like to be able to output the LCS string. So to make it, well, relatively easy to find the actual LCS, not just its length, we're going to store a little bit of extra information alongside our C array. We're going to have a parallel pi array, or a pi table, just like we have our C table. And we're going to store extra information in this pi table, similarly to how we stored extra information in the coin changing problem or in the knapsack problem, the 0-1 knapsack problem, to help us understand how to sort of backtrace from an optimal number to an optimal string itself. So in knapsack, we figured out how to backtrace from an optimal profit to an optimal sequence of items. So we're going to do something similar here, but we're going to try to output the actual LCS. So in order to do this, we want to consider, for a given table cell Cij, we want to consider which table entry was used to calculate Cij. Okay, so let me grab my laser pointer here. So Cij might either be computed from Ci-1, j-1, if we're in this case, if xi is equal to yj, or it might be one of these two cells, C of I, j-1, or C of I-1, j. So we have 3 different cases, and we're going to store information in pi of ij that tells us which cell, which entry in C was used to help us compute this entry, Cij. So pi here it represents the predecessor, the previous cell that we're coming from to get to this cell. So it'll be one of these 3 cells. So there are 3 cases. Either C of ij is going to be equal to C of ij-1, or it's going to be equal to C of I-1j, or it's going to be equal to C of I-1, j-1 plus 1. And I'm ignoring the case where C of ij is equal to 0, because once we're in a base case, we're not trying to backtrace anything. One of the strings has length 0, so there's no more LCS to find. So as long as we're not in a base case, these are our 3 cases. So in case 1, where C of ij is C of I j-1, what we're going to store in pi of ij is just a symbol. We're going to store, just as a string, the letter j. Okay, and that's going to tell us that to get to the predecessor entry in the table, we should subtract 1 from j. So j just represents decrementing j to get I j-1. Okay, so, I mean, we could store this in any number of ways in the predecessor array. I'm just picking an arbitrary way to store it. I'm just going to store the string j, and when we do our backtracing, when we see the string j, we're going to know that that means we should decrement 1 from j to get to the previous entry that was used to calculate this entry, Cij. Okay? And in case 2, where we're trying to get to Ci-1j, I'm going to store I, the string I, and pi ij, to indicate that we should decrement the current I that we're at. So instead of being at ij, we're going to be at I-1j. j. So we're leaving these breadcrumbs, these instructions that our backtracing procedure is going to follow. So backtracing procedure is going to see the string I, and it's going to decrement I, and that's going to help it get to the previous cell as it's tracing its way backwards through the table. And then for Cij, we're coming from Ci minus 1, j minus 1. So we're going to store the string ij, which is just going to tell our backtracing procedure that we want to decrement both I and j to reach the entry that was used to calculate Cij. In this case, Cij is calculated from I minus 1, j minus 1. So we're going to decrement both I and j. And remember, in this case, where we're adding 1, right, that's this case up here in the recurrence, xi is equal to yi. And if you remember, when xi is equal to yi, we're going to include xi in the longest common subsequence. So this is a special case. In case 3, whenever we're in this case and we see an ij in pi, we know that we need to include xi in the LCS. And it doesn't make a difference whether we include xi or yj, because they're the same thing. Okay, so I can show you, I'll show you pseudocode for this modified algorithm in a second, and then I'll walk you through the table examples so you can see in the table that we discussed a couple of slides ago, you can see how we would trace our way backwards. And in that diagram for that table, I'm not going to write I and j and ij. I'm just going to draw an arrow because it's easier to see. So we'll represent j as an up arrow for j minus 1, because remember, j starts at 0 and then goes down in our diagram. And I'll represent the letter I by just a left arrow, because it's going to represent going left. And ij, the string ij, I'll represent as a diagonal going up and left. Just makes it easier to see in the diagram. Okay, so in our example table, I'll just draw an arrow to the entry instead of writing the string. You know, if we were to program, I can't store an arrow in the cell, right? So you got to store some value that I can actually program. So here's the pseudocode for this. So we have not only the array C, but also an array pi. Okay, and we're going to have our base case as usual, where we just implement the recurrence base case, and then we have our 2 loops where we compute C of ij for all of the general case, non-base case entries. And then we have our cases, just as we had when we looked at the algorithm before we had this notion of the pi array. So if xi is equal to yj, then we add 1 and refer to entry Ci minus 1, j minus 1. And we store ij because we need to decrement I and j. If we're in this case, Cij was computed using Ci minus 1, j minus 1, so we set pi ij to ij, which will indicate that when we backtrace, if we want to figure out where Cij came from, you just decrement I and decrement j, right? And then similarly, okay, I think I have an animation here. If I just give it a second to pull it up, my computer's sort of slow. My animation's all out of order. Anyway, here are the 3 cases. So we covered these cases on the previous slide, right? So this is the case where C of ij is C of I j minus 1, right? We store j. This is the case where C of ij is C I minus 1 j. We store I. Okay, so really what's new in this is just that we have this pi array that we're populating alongside the values of the C array that we are populating in the same way as before. And at the end, we return the array C and the array pi. So both tables get returned, and that way, when we want to do our backtracing, we can pass both of those tables to the backtracing, and pi will help us figure out how to backtrace. Okay, so let's see an example of how we would actually run this backtracing algorithm. So suppose we have 2 strings, x and y, and we've reasoned about these strings before. We've reasoned that gvet should be the LCS of these 2 strings. Let's see our table, and here, this is our table that we filled in before, but now I also have arrows, right? So up left represents ij, up represents j because we're decrementing j when we go up, left represents I because we're decrementing I when we go left. So I'm just drawing them as arrows to make it easier to see the path. And if you remember, the bottom right entry here is it's the length of our longest common subsequence. So let's figure out how to extract the longest common subsequence, or some longest common subsequence, because there might be many for a given set of input strings. You know, there can be many subsequences that have the same length, and they're all maximal. So anyway, we'll extract some longest common subsequence using this method. So we'll start here. This arrow says we should go to the left, so we'll decrement I and we'll go to the left. And then the fact that we're going left here means this A is not in the LCS. Okay, we're only saying something belongs in the LCS when we go up left, because that's the case where the xi and yj are equal, and we take that letter xi to be part of the LCS. Okay, so this says up left, which tells us that the sequence so far that we've accumulated of letters, we're going to accumulate these letters, we're going to push them into a string, is t. So we see this up left. That tells us that we're in this case where we're moving up and to the left, and we're adding 1. So we're actually taking this letter t in the LCS. Okay, so we move up left. We're here now, and we see up. So that's not in the LCS. We move up. This k is not in the LCS. We move up. We end up here. We aren't extending the LCS at all. We end up here at a diagonal finally where e and e, so x of I and y of j are equal. So this is going to be this e is going to be in the LCS. So our sequence so far that we're accumulating, if we manage somehow to prepend, because remember, we're tracing this backwards, so we're starting at the last letter in the longest common subsequence. So we have to prepend these. So if we have t, we can prepend e before t. And remember, we're trying to build up to GVET. So we go up and to the left. We end up here. This is an up arrow, so we don't do anything except go up. Then we end up at this up left arrow, which tells us that v, this x of I, which is equal to y of j, is going to be in the longest common subsequence. So we add this v to the sequence. We prepend it to get VET, and we move up and to the left. This left, we don't really do anything except move to the left. And we end up here where finally we see xi equals g, yj equals g. They're the same. We end up taking it in the LCS, and our LCS, once we prepend g, is GVET. Finally, we end up in a base case. If we end up in the first row or the first column, like the 0th row or the 0th column, then we're done because one of the two strings is empty at that point. Okay, so in the end, our LCS is GVET, as it should be. And here's pseudocode for doing this traceback that I just showed you. So first we create a new string, LCS, and then we set I and j to m and n respectively. We start at that bottom right cell. And then as long as we're not in a base case, so while I is greater than 0, j is greater than 0, we inspect pi of ij to see which direction we should go. If it's ij, then we only go up left when we're taking an element into the LCS. So xi is going to be part of the LCS. So we can, assuming that our strings don't have the ability to prepend, we can append, and then we can reverse our string at the end. So we append, and we decrement I and j. And on the other hand, if we saw pi of ij as j, we decrement j. If we saw pi of ij as I, then we decrement I. We just continue until either I is 0 or j is 0 or both. And then at the end, we reverse the string that we've appended. So in our case, we started at the end of the LCS in the previous example. If we appended, we would, so it was GVET was the LCS. We would append t, then we would append e, then we would append v, then we would append g. We'd end up with TVEG, or sorry, TEVG. So we have to reverse that at the end. So we do this reverse step finally. Okay. So what's the runtime complexity, or the space complexity of this algorithm in the word RAM model? Well, our operations are going to take constant time on the entries of these arrays, and let's see, our decrement will take constant time. Decrements are constant time. These comparisons are constant time. This appending, let's say that we can append to the string in constant time. So everything that's done inside this loop will be constant time. And then how many iterations are there? Well, I starts at m and j starts at n, and in each iteration of the loop we decrement either I or j. So we can only have m plus n iterations, each doing a constant amount of work. Okay, so the whole loop is going to take, let's say, order m plus n work, and then lines 3 and 4 will take constant time. Line 2, let's say we have to allocate a string, and let's just say that allocating enough space to hold the largest possible LCS. So the LCS could be the bigger of m or n. So let's say we have to allocate the bigger of those two sizes, and let's say that allocating that string takes time proportional to the size of the string. So let's say it takes time proportional to the maximum of m or n, and we can express that in asymptotic notation as big O of m plus n. So line 2 will take big O of m plus n time. So in total, and then reversing can be done in time that's linear in the length of the string, and the length of the string is, in the worst case, the bigger of m and n, which is order m plus n. So reversing will take order m plus n time as well. So this whole thing could be done in order m plus n time. Well, how about the space complexity? Well, for space complexity, we want to count in the word RAM model the number of words that we introduce in the algorithm that are not part of the input. So we ignore the input. And what words are we introducing? We're introducing a string. Let's say the string has one word per character. And the number of words then for the string will be order m plus n. Then we introduce words for I and j, which is basically nothing, just constant, right? And that's about it. Maybe there's an extra array used as part of the reversing procedure. At any rate, you won't need more than order m plus n space for that. So this can all be done in order m plus n space. And note that when we're computing a space complexity, we exclude the input variables. So even though these are bigger than order m plus n, we don't count them. So this is order n plus m space in terms of words. It's order n plus m words. And the time is order m plus n steps. Oh, what's this? Oh, I think it's a towel rack break. Ah, that looks pretty nice. And it's nice and level. Okay, so the next problem I want to talk about is called the minimum length triangulation problem. So the input for this problem is going to consist of n points, q1 up to qn, in 2D space. So we're just talking about regular 2D Euclidean space. And these points, they form a convex polygon, an n-gon with n points. And we're going to call that polygon P. And we can assume that the points are sorted clockwise around the center of P. So here you can see, if you just imagine the center of P, by the way, because it's convex, the center of P is inside P. If it's concave, then things get weird. But this is a convex polygon. And you can see that the points here are sorted clockwise, right? So 1, 2, 3, 4, 5, 6, 7. Okay, and the goal in this problem is to find a triangulation of P. What's a triangulation? It's a way of cutting this polygon up into triangles that don't overlap one another, right? The triangles cover the whole polygon, but no triangles overlap. So you want to be able to draw these lines that don't cross each other, right? If there was overlap, lines would be crossing each other. So you want to basically draw lines to cut this up into triangles, and there are different ways of cutting up this polygon into triangles. And you want to do this. This is an optimization problem. You want to find the particular triangulation that minimizes the sum of perimeters of the triangles. So, and I say of the n minus 2 triangles here because there are n points. And it turns out that any way of triangulating n points will produce n minus 2 triangles. So here we have, in this example here, which I shamelessly stole from Wikipedia, I have 1, 2, 3, 4, 5, 6 points. This is a hexagon. And we divide this into 1, 2, 3, 4 triangles. Each of these triangulations is 4 triangles. And in fact, every triangulation is 4 triangles if you have 6 points on a convex polygon. Okay, so we're going to take these n points and we're going to find the triangulation into n minus 2 triangles that has the smallest sum of perimeters for all the triangles. So first of all, what's the perimeter of a triangle, right? It's just the sum of the lengths of the sides, right? So for this top left triangle, we're going to sum this side, and this side. Then for this triangle, we're going to sum this side, and this side. Yes, this side is double counted. That's fine. For this triangle, we're going to sum this side, and this side, and this side. And for this triangle, we're going to sum this side, and this side, and this side. And we want to find the triangulation that has the minimum sum of all those side lengths, okay? And the output, rather than going all the way for the complicated version of this problem and having you output the actual triangulation, you can output just the sum of the perimeters that is minimum, okay? So how hard is this problem? Could we just try all the triangulations or something like this? How many triangulations are there? Well, it turns out there are a lot. So the number of triangulations of a convex n-gon is the n minus second Catalan number. Here's what that looks like. And if you actually solve for a closed form, you can show that this is in theta of 4 to the n over n minus 2 to the 3 halves. So this is something like, it's exponential in n, certainly, right? So this is extremely large. For a 100 gon, a polygon with 100 points, you're talking runtime that's along the lines of number of particles in the known universe. So we really don't want to try all the triangulations. That would be incredibly slow, so we're going to have to do something more intelligent. So we won't brute force it. We'll come up with a dynamic programming solution. So first off, we want to try to ask the question, how could we try to decompose this problem into subproblems? So if I have some convex n-gon here, which I've drawn on the right, with points q1 up to qn, consider the edge between q1 and qn. That edge is going to participate in some triangle. When we triangulate this, that edge will be part of some triangle. And of course, that triangle will have a third vertex. So call that third vertex, besides q1 and qn, it'll have a third vertex qk. Okay? Now, for a given k, if I fix that qk, what do we have here? What does our problem decomposition look like? Well, we have this triangle q1, qk, qn, right? And then we have some other parts here, right? We have this polygon here with vertices q1, q2, q3, all the way up to qk, and then back to q1. And we have this polygon here from qk, qk plus 1, qk plus 2, all the way up to qn, and then back to qk, right? So by considering this edge from q1 to qn, which must participate in a triangle, and then fixing the third point on that triangle, qk, we've divided the problem into a triangle and then two other polygons, two other convex n-gons, because this whole thing being convex means that if I take one triangle out of this and consider what remains, I end up with two convex n-gons. Well, not n-gons, but you get a convex k-gon and a convex n minus k plus 1 gon. Okay? And I'm not going to prove that, but anyway, this just comes from geometry. Okay, now the optimal solution to this problem, if we fix this k, like suppose this triangle, for this fixed choice of qk, suppose that this triangle is in the optimal triangulation, the triangulation that has the minimum sum of perimeters. Okay, suppose that's true. Suppose this triangle is in the optimal triangulation. Then the optimal triangulation will consist of this triangle and the optimal triangulations of this polygon and this polygon. Okay? So we can start to see the recursive structure come together, the optimal recursive substructure come together. And if you wonder why this is true, supposing that this triangle is part of the optimal solution, we have to triangulate this polygon somehow, and we want to triangulate it with the optimal triangulation, because if we use a suboptimal triangulation, we can improve our solution by replacing it with an optimal triangulation. Right? The sum of perimeters here has to be minimized, because if it's not minimized, we can improve this. So we're going to have the optimal triangulation of polygon 2, the optimal triangulation of polygon 3, and this triangle, under the assumption that this triangle is in the optimal solution. Okay, but maybe this triangle isn't in the optimal solution. Some triangle is going to be involving this edge is going to be in the optimal solution. So we may just have to consider different choices of QK. Okay, so we're going to consider these separate polygons. We're going to consider the optimal triangulation of them, and now we have our optimal recursive substructure. So let's try to turn this intuition about the optimal recursive substructure and how we can express the whole problem in terms of subproblems into a recurrence relation. So let Sij, we're going to define now our recurrence relation expression, Sij, and we're going to define the semantic meaning that Sij should have. This is the meaning that we're going to try to implement. And by the way, when you're solving divide and conquer problems, you should always start by writing down whenever you define or declare a term here for a recurrence, you should always try to define the semantic meaning, what this should contain. Without this, you have no way to reason about the correctness of your algorithm, because this is the definition that you're trying to actually solve for when you implement this, when you actually write down a recurrence. Okay, so Sij is going to be the optimal solution to the subproblem consisting of the polygon with vertices I to j. Okay, and so we're going to restrict the set of vertices basically, and that's going to give us some polygon, and we're going to try to figure out the optimal solution for that polygon consisting of vertices qi to qj. And just for the sake of making the notation simple, let delta ijk denote the perimeter of this triangle qi, qk, qj, or equivalently qi, qj, qk. Okay, and what is this perimeter? It's the distance between I and j using the usual Euclidean distance formula, square root of, x squared, square root of qi dot x minus qj dot x squared plus q, et cetera, right? It's the usual two-dimensional distance formula. But I'm just going to write it down like this so we don't have, big ugly expressions. So delta ijk is just going to be the perimeter, meaning using the usual Euclidean two-dimensional distance formula, the distance between I and j plus the distance between j and k plus the distance between k and I, right? So delta ijk is the perimeter of that triangle. Now, if a given point qk, or rather, if the triangle defined by qi, qj, and qk is in the optimal solution, so this line here is a typo. I should have written if this triangle, qi, qk, qj, is in the optimal solution. Then Sij, right, the optimal way to use vertices qi up to qj, and these are vertices that are sorted clockwise, right? So here's qi plus 1 all the way up to qj. So if this triangle, qi, qk, qj, is in the optimal solution, then the optimal way to triangulate all of these vertices from qi up to qj is the optimal way to triangulate qi up to qk, right, that polygon, plus the perimeter of this triangle, delta ijk, plus the optimal way to triangulate the remaining piece from qk all the way up to qj, this polygon, right? So S of ij is S of ik plus delta ijk plus S of kj. Now the problem is we don't know the optimal k, right? We know that this edge so if I back up one step, this edge between I and qi and qj will be involved in some triangle, right? But we don't know if if this should be qk, or maybe this point here should be qk, or this point here should be qk. So we sort of have to try all of the different possible k values between I and j, and we want to maximize over all those possible k values, right? So here, if we choose qk to be this point here, that's this diagram, right? And in fact, in this case, we have this triangle, and then we only have one remaining polygon. So it's not necessary that there will be two polygons, right? There might only be one extra polygon besides our triangle, right? If it's the leftmost triangle, or here, if it's the rightmost triangle, there's only one polygon on the left of it. Okay. And then this is all the possibilities, right? We try all the different possibilities for choices of QK, and for each of these, we're going to compute the recurrence that we saw on the previous slide that assumes that K is optimal, right? And for one of these choices of K, this will be a triangle that appears in the optimal triangulation. So here's K equals I plus 1, K equals I plus 2, I plus 3, and so on, all the way up to J minus 1, right? And this next point is Qj, of Qi, Qj. Okay. So here we're going to have S of I, K, where K is just I plus 1 in this degenerate case. This is not actually a polygon, right? The polygon to the left of this triangle doesn't actually exist, so it's just going to be 0. And our SKJ is what we're computing here on the right. And then, similarly here, this is our SIK, so QI all the way up to QK. And then here's our K all the way up to J, and so on. And then here in the final diagram, we have S of I all the way up to K, and in this case, where J is just K plus 1. So we have K and then K plus 1. This is a degenerate polygon. It's a two-gon that has 0 area, right? So there's no need to triangulate here, so this is going to contribute 0, because there's nothing to triangulate. This will contribute 0 to the result. Okay, so we want to maximize over all these choices of K. Here's our recurrence. S of ij is going to be, this is the optimal way, this is the optimal sum of perimeters for the optimal triangulation of the polygon consisting of points Qi up to Qj. Okay, so these were points that were all consecutive and part of the original polygon, which was convex, and they were all sorted clockwise, right? So it's going to look something like this. That's going to be the maximum for K strictly between I and J of SIK, this part, plus delta IJK, this part, plus SKJ, this part. And this is a reasonably well-defined formula. If J is greater than or equal to I plus 2, if J is only I plus 1, then, well, here we saw what happens, right? Here, J is K plus 1 here, and there's a degenerate polygon. It's a two-gon that doesn't contribute anything to the triangulation. So if we have like K plus 1, in this case we have like I plus 1, then we should just make the perimeter 0. The contribution to the perimeter of that degenerate two-gon is 0. So if J is greater than or equal to I plus 2, meaning we can actually make a triangle, then this is the formula. Otherwise, if we can't make any triangles, then 0 is the formula. Okay, so here's our recurrence. Now, how do we fill in the table? So first of all, our table will be defined in the way that you might expect. For our recurrence Sij, we're going to have a table Sij. It's going to be I equals 1 up to n, and then for each of those i's, you have j equals 1 up to n. Let's draw it like this. So here's our table as a square, and it is a square n by n in size. Let's draw our j's going to the right, increasing to the right, and our i's increasing going down, just for the sake of the diagram. And we have two different formulae here, right? So if j is greater than or equal to I plus 2, well, we need to look at the line j equals I plus 2 and figure out which side of the line we're on. So here's j equals I, right? It's a diagonal line through the diagram, through the table. Where's j equals I plus 2? Well, if we start out at some point in this line where j is equal to I, and we go to the right, j is increasing. So j is getting bigger than I as we go to the right. So we're going to shift this line to the right by 2 units, and that's going to be the line j equals I plus 2. Okay? And for j greater than or equal to I plus 2, we're talking about everything to the right of this line, okay, of this orange line. So everything in here satisfies j greater than or equal to I plus 2. So this is where we're going to use our complicated fancy formula in this blue region. And in the gray region, we're going to use just 0, right? So this is all going to be zeros. So let's consider the data dependencies for a cell ij that's in this blue region, because we don't need to think about data dependencies for anything in this gray region. It's all just 0. Well, the dependencies for Sij are going to be Sik and skj for all the different k. And well, what are the k values? It varies from I plus 1 up to j minus 1. So let's think about these two expressions, sik and skj for all these different k values. So sik, well, k starts at I plus 1. That's si I plus 1. And it goes all the way up to j minus 1. So it's going to go from si I plus 1 to si j minus 1. Okay, si I plus 1, si j minus 1. So this is sij. Sij minus 1 is just to the left of this. Sij minus 2 is to the left of that still. And we keep going until we get all the way to si I plus 1. Okay, which is just to the left of this line where j equals I. Okay, so this black region here is for sik. This is all the dependencies that are induced by the term sik in this recurrence. What about the term skj? Well, for skj, we're varying the first term, right? So it's going to be s of something j, and that is going to vary from I plus 1 to j minus 1. So we're going from s of I plus 1j to s of j minus 1j. So where does this appear in the diagram? Well, here's sij. Si plus 1j is going to be 1 lower, si plus 2j, and so on, all the way up to sj minus 1j. So we're going to go all the way almost down to j comma j, but only to j minus 1 comma j. So it's this black region here. So this red box depends on these two black regions. Okay. So looking at this diagram, everything in this black box has a larger I value than the red box, right? This is all s something greater than I, comma j. Okay, so we depend on things with larger I values, and we depend on things with the same I value, but with smaller j values. That's what this diagram is telling us. Larger I, or same I, but smaller j. Okay, so what's a correct fill order that will respect the constraint that when we compute ij, we want to make sure everything we depend on has already been computed? I'll give you a second to think about that, so you can pause and figure that out. Okay, I'm going to assume if you wanted to figure that out, you've paused and done so. So we depend on larger I, so we should make sure that larger I rows are computed first. Okay, so we're going to iterate from large I down to small I, and then within a row, we want to make sure that smaller j are already computed. So we want to compute smaller j's first, so from small j to large j. So for I, we go from n down to 1, and then within a row, for j, we go from 1 up to n. Okay, this fill order will make sure that our dependencies have already been computed when we compute ij. Okay, so I'm not going to show pseudocode for this because it's fairly straightforward, and it's a good exercise, I think, to translate this recurrence into pseudocode. But let's talk about the runtime, and we don't actually need the pseudocode really to at least have a rough discussion about runtime in the WordRAM model. So first, let's talk about the number of subproblems. How many subproblems are there? Well, we have a subproblem for each ij. And, well, there are n squared ij, parameterizations of ij. So there are n squared subproblems. How much time does it take to solve subproblem sij? Well, for sij, we need to do some constant amount of work for each k. How many k's are there? There are j minus I, approximately, k values. So this is order j minus I, and of course, if we're only looking for a big O expression, j minus I is less than or equal to n. Right? J minus I is less than or equal to j, which is less than or equal to n. So, this is big O of n to solve a subproblem naively, and there are n squared subproblems. So we can trivially get order n cubed runtime, at least if we only care about a big O expression. If you want to show big omega, then note that at least n over 2 minus 2 squared subproblems do omega j minus I work. How am I getting this funny expression? Well, in order to show a big omega, I need to show that there are order n squared subproblems that do something like omega n work, right? So we only do constant work in the base case, so we need to ask the question, how many cells are there that aren't this base case? How many of these cells are there where j is greater than or equal to I plus 2? This is where the 2 is coming from in this formula, right? So take the diagonal, right? That's the line j equals I, shift it by 2, that's this minus 2, and then square that, and it's order that many subproblems that are in that triangle to the top right. You could do a more precise calculation if you like, if I pop up a little bit here, to calculate how many cells there are in this blue triangle, because that's how many cells are doing order j minus I work. And then with a little bit of care, you can do the legwork here to show that there are enough of those subproblems that do order n work in order to justify an omega n cubed complexity to finally get a theta n cubed complexity. So I'm not filling in the details here because the computation gets kind of annoying and I don't want to get bogged down in mathematical details. Certainly, it's easy to argue that this is big O of n cubed time. Okay. Incidentally, this happens to be polynomial time in the input size, but I want to make the point that basic runtime analysis doing this order n cubed analysis does not require an argument that this is polytime in the input size. Like, you only have to talk about whether this is polytime in the input size. You only have to reason about the input size if we ask you to prove something along the lines of that claim, that this algorithm is polytime in the input size. If we ask you to prove that, then you need to think about the input size. Otherwise, if we just ask you to argue about the runtime, you don't need to think about the input size, because you notice I didn't have to say anything about the input size in order to give this runtime order n cubed. Okay. The last thing I want to talk about very briefly is something very similar to dynamic programming, but slightly different, memoization. So this is an alternative to dynamic programming that has very much the same goal. You can transform a dynamic programming algorithm into a memoization algorithm and vice versa. So problems that can be solved with DP can be solved with memoization. It's just two different expressions of the same idea. And sometimes memoization is more natural for a particular problem, and sometimes dynamic programming is more natural for a particular problem formulation. When we ask you for a dynamic programming solution, we don't want you to provide a memoization solution. We want you to instantiate a table and show how to fill it. But I wanted to let you know about memoization because I think it's good to know about. So the idea in memoization, like in dynamic programming, is to remember which subproblems have been solved. The difference is, in dynamic programming, you want to make sure that you compute your subproblems from the bottom up in an order such that whenever you want to compute a particular subproblem, all of its dependencies are already computed. In memoization, rather than pre-computing from the bottom up, we're going to start from the top down. And whenever we want to compute a subproblem, we're going to recurse. So this is a recursive problem. Or it's a recursive algorithm we're going to come up with. But whenever we return from a recursive subproblem, we're going to save our return value. So the next time we try to recompute the same subproblem, we're actually just going to reuse the value that's already been computed. So we'll cut off the recursion tree at that point. So rather than recalculating recursive subproblems over and over again, we'll just look them up in a table. The difference is we're not going to pre-compute the table. We're going to compute the table as we return from recursive calls. Okay. So let's see what this looks like. And I'll just do it with a toy problem. We're going to do this with Fibonacci numbers. So we saw a divide and conquer solution to Fibonacci numbers. Let's see how you would memoize the results in that divide and conquer solution. So first of all, in order to do memoization, you do need a table that you're going to save your results in. And that table should be global. It should be external to the recursive procedures that you're calling. Or perhaps you could provide it as an argument to your recursive procedures. At any rate, it needs to continue to persist once your recursive procedure returns. So I'm going to declare it here as a global. So we're going to have this M array that's a global memoization array. And we're going to try to use it to compute Fibonacci numbers up to n. So the array is going to have size n. And I'm going to initialize all of the contents of the array to -1. What does -1 mean? Intuitively, it means I have not yet computed this table cell. So this is what's going to help us distinguish between cells that are computed and cells that aren't computed. We're using the fact that Fibonacci numbers are never negative. Okay, so let's see how we would, so we initialize the table and then we call the recursive Fibonacci procedure, which has a small modification. So here, let's see what's different about this from the usual recursive Fibonacci procedure. First, we have the base case. If n is 0, we return the 0th Fibonacci number, which is 0. If n is 1, we have our second base case where we return the 1th Fibonacci number, which is 1. And then, in the general case, we want to now compute the nth Fibonacci number recursively. But before we go into that recursive computation, we want to check, has this nth Fibonacci number already been computed? So we check in our table, has it already been computed? If so, then we just read the pre-computed value that was already computed, and we're going to return that value down here. Otherwise, if it hasn't been computed yet for this particular n that we're computing in this recursive call, we're going to make our recursive calls here, 1 and 2, as we do in the usual recursive Fibonacci algorithm. We're going to sum up the results, and we're going to, before returning, save that result in our table as the nth Fibonacci number, and then finally we'll return the value that we computed. So how does this make a difference in the recursive computation? Here on the right, we have the recursion tree for the 5th Fibonacci number, and this is for a naive recursion. Let's see how this recursion tree changes once we introduce memoization. So it starts out the same as in the recursive algorithm. We make our 5th recfib call, and it's going to make recursive calls to F4 and F3 to compute F4 and F3. So we recurse into our F4 call. And then that F4 call is going to recurse into an F3 call. F3 call is going to recurse into an F2 call, which is going to recurse into an F1 call. And then finally, this F1 call is a base case, so we're just going to return. And when we return, now we're going to pop back up into computing our F2. So our first call here on the left in F2 is going to return. So we now have 1 here. Then our second call to the right, we're going to make that recursive call. It's a base case, so it's just going to return 0. And now we've executed both of those calls. We're in this we've popped up back up the stack into this F2 call. We're going to add those two numbers together, save them in F. We're going to save those in M2. So M2 is now computed, and we're going to return that result. So now when we pop up to F3, we're going to pop up the stack back into our F3. It's going to make a recursive call to the right. That's, of course, already done. I wrote already done here, but really that's a base case. So it's just going to return 1, and we're going to take our F2 and our F1, we're going to add them together, and we're going to save it in M3. Okay, so we're saving M3 now. M3 equals 2. We're going to pop back up the recursive stack to F4. It's going to make a recursive call on the right to F2. Now, when it makes this recursive call to F2, it's going to see, is this base case 0? It's not. Is this base case 1? It's not. Is this pre-computed? Yes, F2 is pre-computed. So it's going to look up the pre-computed value, and it's not going to do any further recursive calls in that subtree. So we're going to take 2 and F2, which is 1, and we're going to add them together. We're going to get 3. And before we return from our F4 recursive call, we're going to save it in M of 4. So now when we pop up the recursive stack to F5, it's going to try to make a recursive call on the right looking for F3. And F3, that call is going to see, am I base case 0? No. Am I base case 1? No. Have I been computed already? Is M3 already computed? It is. We computed it down here. So we're not going to do any recursive calls in the subtree. We're immediately going to return the value of F3. So what's interesting about this diagram is that our recursion on the left all gets finished, right? We all actually execute the recursion on the left. But every right child, by the time we recurse on the right, at least above this F3 tree, if we made this tree way bigger, we'd see as we go up and up and up, all these right children, these entire subtrees are being cut off. They're pre-computed, right? Because by the time we compute the left side, we've already computed the right side, because the right side is the smaller subproblem, n minus 2, when on the left we've computed n minus 1. So basically, this reduces this recursion tree almost to a straight line along the left, where all of our left-leaning recursive calls work out, but all of our right-leaning recursive calls, their subtrees all get pruned. This reduces the amount of recursion from exponential in n to linear in n. So you get the exact same exponential speedup that you get from dynamic programming by doing memoization. Okay, so with that, I guess I'll end the mandatory material for this lecture, but I encourage you to check out the bonus clarification material that I've included in the last few slides. Hopefully it'll just help solidify some of the discussion of different models and a discussion of how to calculate input size that's been going on Piazza in a more cohesive way than the disjointed discussions there. So with that, I'll look forward to teaching you guys, at least in the capacity that I will be in creating assignments and finals and marking. I hope you guys enjoy the lectures by Anna from this point on. All right, thanks guys. Take care.